magnetospheric accretion and outflows in T Tauri stars.
Outflows, no outflows. So thanks to organizers for inviting me, so letting me broaden my knowledge about so many interesting objects. So what I'm going to present is quite a broad review of different numerical magnetohydrodynamic models of the interaction of the magnetosphere of a classical T Tauri star with its surrounding accretion disk. How do you move? Yes. The presentation will be divided in three parts. First, I will try to characterize the essentially dynamical constituents that we usually find in a numerical simulation of a star disk interaction magnetospheric model. Then I will show some results of some people who tried to extract synthetic observations, synthetic line profiles from these simulations in order to be directly compared to observations. And I will conclude trying to compare the variability produced in these models with the observed variability. So what are the building blocks of typical numerical simulations with star disk interaction? We have accretion components. Of course, there is an accretion disk. At some point, this accretion disk is truncated by the magnetosphere of the star, and it starts to form accretion columns onto the surface of the star. And then we have ejection, usually ejection in different flavors. We have stellar winds. Stellar winds exploit the open magnetic flux, which is directly anchored onto the surface of the star. We can have disk wind that exploit the open flux anchored onto the accretion disk. And then we have an intermediate class that I like to call magnetospheric ejection. Some other people, Marina Romanova, likes to call it conical winds. I think that we are exactly talking about the same things, just trying to confuse you a little bit. And these magnetospheric ejections, all conical winds, they use magnetospheric lines that are still connected. They are still connecting the disk with the star. So it's sort of intermediate class between the two. Okay, about accretion. So usually in these simulations we have quite a rough, simple model for the accretion disk, which is typically modeled as an alpha viscous accretion disk, with some notable exception, always by Marina Romanova, try to include an MRI active disk accreting onto the magnetosphere. The alpha torque or the MRI turbulent torque usually is not the only torque driving accretion. Of course, since there is the stellar magnetosphere, the large-scale magnetic fields tend to add another torque on top of the disk. Then the disk is truncated at the magnetospheric radius and starts to form the accretion column, I will see in these beautiful results, always by Marina Romanova. The accretion funnel accelerates, becomes supersonic, but not subalvanic. The magnetic field, the stellar magnetic field is very, very strong, so it's not possible to become subalvanic, and impacts the stellar chromosphere essentially at freefall speed, forming strong accretion shock. The accretion shock in these particular models is obviously not resolved. I mean, it's totally unresolved with the typical resolution that we can afford. One important point, in these models we cannot include, at least up to now, we're not able to include gas chemistry, presence of dust, and we have usually a very simplified equation of state like barotropic or something like that. Barotropic in the sense the temperature is proportional to the density to some power. So going to outflows, some considerations about stellar winds. Classical T Tauri stars are slowly rotating stars, typically below 10% of the breaker speed. So there is no centrifugal thrust. The magnetocentrifugal mechanism, Blanford-Pay, cannot work for these kind of stars. The thermal driving, the thermal pressure as an acceleration effect, is essentially ruled out at least for mass loss rate larger than 10 to the minus 11 solar masses per year. That would produce too much emission, in particular too many X-rays, totally incompatible with the X-ray emissions of these stars. So if you want something more massive, we have to add some other ingredient. One of the propositions, or the most popular propositions, is to have essentially alpha waves, probably triggered and amplified by the impact of the accretion columns on the surface of the star. In this way, we can also introduce a link between accretion and ejection also for stellar wind. Sean, Matt, Pudritz, they like to call this kind of scenario accretion-powered stellar wind. Somebody dared to try to estimate how much energy, how much momentum you can extract from accretion with this mechanism. Stephen Kramer essentially put some quite strong upper limit on the mass loss rate of the stellar wind at 1% of the accretion rate. Usually what we do in the numerical simulations, we try to trying to be conservative. We model light stellar winds, so stellar winds with low ejection rates. But since we cannot simulate directly these complicated mechanisms, we still treat them as thermally driven. So they're extremely hot, at 1 million degrees hot. We know that is not reasonable, but there is no other way we can today that we can model these kind of winds. Anyway, in the simulation, since they are, these winds are light and have also very large magnetic averams, they provide a high velocity component in velocity pattern of the system. The magnetospheric ejections, or conical winds, as you prefer, is a dynamical phenomenon associated with the quasi-periodic inflation, opening, and reconnection of the field lines still connecting the star with the disk. When a field line connects the star with the disk, due to differential rotation, start to develop a lot of toroidal field. This provides an additional magnetic pressure component that opens up and launches these outflows at essentially at mid latitude at 45 degrees, let's say, something like that in the star disk system. Since they exploit magnetic field lines that still connect the star with disk, they can exchange mass energy and angular momentum with both. Typically, I mean, this is really sort of model dependent, but they can extract from between 1 and 10% of the mass accretion rate, but they extract it from a relatively tiny region located around truncation, more or less in the spirit of the X-wind, if that sounds familiar to you. They can be an intermediate to fast velocity component. This is really parameter dependent, but they can be as fast as the stellar wind in principle. As I was saying, they are quasi-periodic, and because it's based on this inflation reconnection quasi-periodic mechanism, and on a large scale, they proceed as plasmoids. So they're ballistic, so they proceed essentially in a straight pattern. That's why Romanov, I think, likes to call them like conical winds. And finally, the disk winds. Okay, not all kind of disk winds, just the disk winds that we usually observe in these simulations. This is actually a simulation that shows the presence of all the outflows at the same time. So here's the stellar wind. You see here these blobs are the conical winds, the magnetospheric ejections. And then you see there is some ejection also coming from the disk. This disk wind exploits the open flux. The open flux is a leftover of what remains of the original stellar flux. In that sense, the disk, the magnetic field in this part of the disk is relatively weak. So this is the beta parameter, the ratio between the thermal pressure to the magnetic pressure is relatively low, definitely lower than what you have around the truncation, where you are more at equipartition. You can have, again, something between 1% and 10%, very typical accretion rates, but in this case, you extract it from a much wider area, not in the small area as the conical winds. They have a small magnetic average. The alpha surface is pretty close to the disk surface. So in general, they provide an intermediate to low velocity component, and you see it here. If you see just very visually, if you compare the size of the green arrows here and here, you see that it is much lower velocity components. Anyway, they sensibly contribute to the angular momentum transport, so it's an extra torque that provides accretion on top of the alpha viscous torque. And where am I? Okay, yeah, so I gave this general introduction about all these dynamical components that we observe, that we find in these numerical models. As I was saying, I mean, what really we cannot constrain with these models are essentially the thermal structure of these solutions. And as I was saying, usually we use, for example, a barotropic equation state. How bad is that? Actually, I don't know. But if you compare, for example, this is the typical temperature profile inside an accretion column provided by the Muserl semi-analytical models that are commonly used to interpret the line profiles of the accreting line profiles. And here we have the density profile inside the accretion column of a numerical model. The temperature is proportional to the density, to some power. So instead of having this nice maximum of temperature, if you take the temperature out of our simulations, we actually have a minimum. So, well, just take that in mind. As I was saying, we model the stellar winds are thermally driven. So their temperature is around 1 million Kelvin. That is totally unreasonable. So in some way, we have to get, if you want to extract a synthetic observation, we have to get rid of that larger temperature. We cannot afford really to couple directly a radiative transfer computation with the simulation directly. So we do everything they do for the moment. They do these kind of things for the moment. They do everything in post-processing, but you have to make some assumptions about the thermal structure in order to derive the synthetic observables. So something even very simple, you put a threshold to the temperature, it cannot be larger than 10,000 Kelvin, something like that, or you rescale the temperature profile that you get from the accretion column. How good are all these approximations? Well, the results are final and not too bad. Maybe the results are not that sensible about the thermal structure. If we make some reasonable assumptions, they are not that sensible to the hypothesis that we make about the thermal structure. So here, Silvia Lenka tried to derive some synthetic observables from some magneto-hydrodynamic models, especially devoted to DSAR V21 focus, the characteristics that have been put directly into the dynamical model. And here you see in black are the synthetic line profiles, in red are the observed one. So the agreement is not perfect, but is not too bad. We see, for example, something that does not agree completely. For example, you have these redshifted absorptions that are out of phase, the model, with respect to the observation. So there is some mismatch in the geometry of the accretion column. And one systematic error is that you underestimate the flux that you have in the blue wing, pointing maybe once again to a different structure, or maybe you are missing some emission coming from an outflow. So going to outflow, so a synthetic observation of stellar winds. Actually, in this case, I cannot compare any numerical MHD model with the observations because commonly stellar winds are not included in the MHD simulations, but we are working on it. So what I'm comparing here is a sort of semi-analytical model developed by Ryuichi Kurosawa. And what he tried is essentially to test the Susan Edwards predictions about the line profiles of these helium-1 line profiles, which is very sensible both to accretion and ejection. Essentially, her prediction is that stellar wind in systems that we see pole on are characterized by a wide and pretty fast extending to large velocities, blue shifted absorption. So in a sense, when you look at a star on the pole, you see the full accelerating region from 0 to the terminal velocity of your outflow, and that gives you this broad absorption. That is an intriguing idea, but for example, for this particular model, for that particular star, Ryuichi had to assume quite a massive stellar wind with a quite high alpha rate, definitely larger than 1% of the accretion rate, and a relatively cold one. And this, from a theoretical point of view, poses several questions about the nature of these stellar wind. The second part of the Edwards et al. Prediction is that if you see the system edge on, your line of sight will go through any kind of disk ejection, and since you will see a narrower range of speed, your blue shifted absorption should be narrower. This time, Ryuichi tried to model that kind of profile with a semi-analytical model, but he also tried to derive line profiles from full MHD models. And in both cases, he found a pretty good agreement with the model, between the model and the observed profile, the model and the observed profile. The drawback of this work, which I find absolutely fantastic, is that, again, from a theoretical point of view, is quite difficult to disentangle between, you lose the details about the model. I mean, crude, essentially, for me, this shows that a crude, simple model or a very complicated MHD simulation could provide you, essentially, the same line profile. Okay, so last part of the talk, the third part, variability. Variability in T Tauri stars comes in different time scales. We saw it already yesterday that we can characterize, and we can see variability from the hour timescales to the year timescales with different amplitudes, while the hour timescale is sort of a small amplitude. The main variability is in the days, weeks regime. That means that most likely is something related to the rotation of the star. And there is also year-long variability. That year-long variability is something that we cannot afford in numerical simulation that typically can handle just with like months timescales. And this variability can come in different flavors. So here we find some examples of different light curves taken by Steve and Carr with a Coral survey. So we have very periodic sources. That's like a spot-like rotating kind of object. We have very irregular objects which they show variability with different amplitudes in different timescales, totally non-periodic. And then we have the dippers, which at least like the AA tau-like, they are quite periodic, and they show dimming events, which are essentially synchronized with the stellar orbital period. So what kind of variability these simulations show, and how can we compare to these kind of results? All the simulations show an intrinsic variability. What I mean by intrinsic is just a variability associated with some pulsed accretion. So you can see it also in axisymmetric models. It's totally not related with the full 3D complexity of the system. And I realized that the easiest the main mechanism that controls this variability is how you go from the disk accretion to the column accretion, because those are two, from the MHD point of view, those are two very different regimes. In the disk accretion, essentially you have to go, you are accreting perpendicularly to the magnetic field line. So in some way you are dragging or diffusing through it, while in the accretion columns you flow parallel to the magnetic field line. So the way you go from the two regimes, and the way you go from the two regimes in these numerical simulations can be controlled by dissipation, by the development of instability, turbulence, interchain instability. That controls how you go from disk accretion to column accretion, and in the end how it characterizes the intrinsic variability of these simulations. For example, here there is forget about all these lines, just look at this one. This is a versus time, the variation of the accretion rate in one whatever simulation. That it's a simulation that assumes some magnetic diffusivity in this transition region, and in this case, you can produce quite rapid. This is in units of the orbital period of the star. So these are sub-day oscillations, not very large amplitude, less than 50%. While, for example, if you reduce this diffusivity that allows you to accrete onto the accretion column, this is the second example taken from one of Romanova's simulation, you have to essentially pile up the accreting material at the truncation radius. At some point, you have a burst of accretion onto the stellar surface. And in this case, you have a very large amplitude in variation. This is a factor essentially 4 in variation of the accretion rate, and this time scale is essentially it's comparable to the orbital period of the star again. So just playing with dissipation of your simulation and things like that, you can reproduce, even with axisymmetric models, a wide range of variability. There is also a specific variability that is found in the numerical models of the propeller regime. A propeller regime happens when the truncation radius gets too close to the co-rotation radius. In that situation, the stellar centrifugal barrier makes accretion difficult, not impossible. Sometimes you have these strong magnetospheric ejections that push matter in, but then they, when the matter accretes, the magnetospheric ejections, the ejection goes down, so the disk is pushed back. And this system starts to form these accretion ejection cycles. So this is characterized by an extreme variability. So for example, here you have an example of a system where in time the accretion rate goes down, so the truncation radius goes towards the co-rotation radius. At some point enters this propeller regime. The amplitude of these oscillations is huge. It's more than 1 order of magnitude, and the time scale again is a few stellar period time scales. This variability, just from a point of view of these models, could be expected in AA tau-like systems that are truncated very close to the truncation radius. But as far as I know, such an extreme variability has never been observed. So most likely, my feeling is that this kind of propeller variability is probably amplified by the axisymmetric approximation. Nobody tried to simulate propeller in 3D, actually. On the other side of the variability, instead of truncating your disk very close to the co-rotation radius, you truncate it very very close to the stellar surface. And in this regime, it has been shown that your system can go into an unstable accretion regime, in the sense that instead of forming two very ordered accretion stream onto the surface of the star, your accretion pattern is fragmented due to an interchange instability and proceeds in tongues going through the magnetic field onto the surface of the star. In the unstable regime, the light curve becomes much more stochastic, so it's kind of, it resembles the idea of these irregular, very irregular sources, and you have a persistent redshift and absorption, not seen as a particular phases. Also, as the propeller regime, some stars, if you just take the characteristics, magnetic field, truncation radius, rotation radius, they could be in this regime. This is just an example. It's again V2129 of Fucus, but they're not. Maybe the instability criterion is a bit too strict, or maybe the multipolar components that are not taken into account in these simulations plays a role in reordering the accretion streams. Who knows? Last type of variability that's being considered in the simulations, something related to the dippers. Once again, Marina Romanova did a very, very interesting and complicated paper. Showed that the uninclined dipole triggers these large warp it's essentially a bending wave, a body wave, displacing really the midplane of the disk out of the midplane of the system. And this bending wave, this warp wave, seems to corrotate with the star, especially when you truncate the disk close to the corrotation radius. This really resembles the cartoon that Jérôme Bouvier proposed to explain the variability of A tau. And actually, they also showed that when you truncate the disk farther in the corrotation radius, the inner warp can get smaller or can even disappear. Maybe they are trying to force all the pieces together. But for example, this is this recent paper by Sylvia Lenker about this source, KCF15, seems to be really, and more or less like A tau, seems to be a system where the truncation radius is very close to the corrotation radius, and the other ingredient that absolutely we not take into account in the numerical simulations, but you need dust there in order to produce these absorptions. It seems that the sublimation radius is very, very close in, below the truncation radius, below the corrotation radius. Everything seems to more or less fit together. So as usual, I talk too much, so I will leave a brief summary there, and I thank you for your attention.
Questions, please?
I have a question. When this is a paradigm for T Tauri stars, where we have a magnetic field from the star that we can measure even. Now, most of the huge solar stars that we are discussing are A-type stars. What we have to change in our views of these winds when we try to understand the possibility of winds in A-type stars?
Oh, wait, okay, just for the wind part, okay.
Yeah, for the wind.
There is, and it's probably related also to the accreting part, but the main parameter, at least for magnetically centrifugally driven winds, is the intensity of a magnetic field, not the stellar one, the field that is inside the disk. That controls everything. And for her big stars is unconstrained as much as is unconstrained in classical T Tauri stars. So from that point of view, is rather, very, very open question. I mean, it's very hard to put constraints.
Yeah, I mean, my view, which is very naive, is that we can apply the same concept of the disk wind to A-type stars.
Yeah, no, I don't see we shouldn't. Yeah.
Everything else must be different, but there may still be a stellar wind due to radiation pressure, due to something else.
I mean, there is always a stellar wind. I mean, the sun has a wind.
Yeah.
Okay, it's really a matter of mass flux and things like that. But in that case, and especially the mass flux, probably strongly depends on the magnetic activity of the star. So,
Please.
First, a comment about time scales. Sometimes very short flares are observed in T Tauri stars, second scale. And may these magnetospheric ejections be the source of very short flares?
Short in what? Seconds. Wow. Oh, that's very, very, very short. And what kind of flares are you talking about? I mean, bad or what kind of flare in which, I don't know, an X-ray flare?
No, optical.
Optical. Oh, on that timescales, I have like hard time say it. For example, I mean, typically what you would expect, because the periodicity, and it's longer than 1 second, but the periodicity, what you expect from these, periodic reconnection events, I would say naively, it's X-ray emission. So you can see X-ray flares associated to these mechanisms, but second scale flares in optical I have.
But in USAT players, primary mechanism is also X-ray and then X-ray.
Okay. So if they are linked, if you can sort of link the optical flares to the X-ray ones, could be.
Please.
May show please
Yes.
slide with so just so probably your
Because
on the
picture slide.
session I see it. So I
Picture
would
slide.
like не
Not
что.
This one.
Куда? Ага, давай. Так, еще дальше давайте. Могу знать. Oh, this one. So, what about magnetic braking? Magnetic locking. So, I see these pictures, I see this many times.
Yeah.
Show me, please, these magnetic field lines which connect the star with the disk and decelerate. And
Is the yellow one?
magnetic, which one? Show.
The yellow one. Where is the yellow one?
No.
Yeah.
So you mean this is out of rotation radius, this line?
Oh, actually, the thing is, the rotation radius of this system is around here, so it's quite close to rotation. You have to also keep in mind that this disk is not Keplerian anymore. So you can receive a braking also inside the rotation radius because the disk is not Keplerian. So you can start to that.
Thank you very much. So you're the first honest theoretician. So you said, well, we use 1 million wind, but there is no such wind. So we use, in fact, not magnetic diffusivity, ideal MHD, but instead this is numerical viscosity when you use to have penetration of disk. So
I will put it on my CV. I will put it on my CV. Sergey Lamson said that I'm an honest theoretician.
Other questions? No. No more questions. Thank
Thank
you
you.
very much.